So for this example, we want to look at a question. How many binary functions are there, right? So we talked about a unary function means that there's one input. So how many binary functions are there? Well, if we go back an example when we were looking at the cardinality of the cardinality of the function x to the 3, right? 0, 1. So remember that? And what was that? Well, that was 2 to 2 to the 3. We're looking at f of x squared, right? Because we're going to have two inputs, a tuple to our binary function. So how many is this going to be? Well, based upon what we learned before, this is going to be 2 to 2 squared, which is going to be 2 to the 4, which is going to be 16, right? So there are 16 binary functions. Now we can eliminate some of them right off the bat, right? We have two constants. We already know about those. Remember we had our identity function, right? Let's call our inputs, I know traditionally we label them x sub 1 and x sub 2, but to make it easier, let's call them p and q, right? Those are our two inputs to our binary function. So we have the identity for p that ignores q, and we have the identity for q that ignores p. So that's two functions for that, right? I'm going to run out of space. I'm not real good at this. Identity. And then we have our negation. And we have our negation for p that ignores q and a negation for q that ignores p. So we have two negation. So what we end up with is 16 minus 10, or 16 minus 6, 16 minus 6, which means we have 10 potential binary functions. We don't, we're not going to name all of them and have special definitions for all of them. We're going to talk about three really common ones, and, or, and exclusive or, because those come up a lot. Now, so far, when we started this, I said a function is whatever we decide it is, right? We define our own functions to map however we want them to map, which is different from the way that you've used functions in all your math classes in the past. We're getting into those functions now. So far we've defined identity and negation, which are two common unary functions. Now we're going to talk about and, or, and exclusive or. Three common binary functions. But, I want you to understand there are 10 unique binary functions. We are just dealing with 3 of them that are of interest to us. So interesting that we give them a name. That's the gist of it. So first, let's continue using p and q as our inputs instead of x1, x2. It's a little bit more intuitive. So our two inputs are p and q. And because, remember, we want to cover all possibilities, so let's say we have p, we have q. I'm going to draw a line. So the first possibility is that p is 0, q is 0. Then we have p is 0, q is 1, p is 1, q is 0, and both p and q are 1. So these are all the possibilities for our two inputs. Binary functions, two inputs. Now we want to look at our kind of common functions. The first is going to be and. Sometimes you will see and depicted as the ampersand. When we do it in discrete math, we usually do p and q. And that is not the caret symbol that's on your keyboard. That is, I don't know what the mathematical name is, but it's a pointing upwards triangle, right? That is how we're going to depict it in this class. Honestly, I don't really care. Like if you want to use the ampersand when you write stuff out, it doesn't really matter. But know that the book is going to use this notation. Okay. So the rule for AND is P and Q is only 1 if P and Q is 1, right? Which means down here, P and Q is 1, which means the output of the function is 1. In this case, one of them is 0, so the output of the whole function is 0. One of them is 0, the output of the function is 0. Both of them are 0, but at least one of them is 0, so the output of the function is 0. That's how AND works. Pretty straightforward, right? Let's take a look at our next one, OR. So OR, commonly in programming, OR is depicted with the bar symbol, right? In discrete math, we usually write the triangle pointing down for OR, right? So OR is 1 if P or Q is 1. You see where these names come from? They're, mathematicians. They're not real creative, right? So here, one of the, P is 1, so is Q, but because, P or Q is 1, the output's going to be 1. In this case, P or Q is 1, the output's going to be 1. P or Q is 1, the output's going to be 1. In this case, neither P nor Q is 1, so that's going to be 0, right? And what you may notice, they're not opposites. People think of and or as opposites, but they're not, okay? They're two different functions that are interesting to us a lot. And the final one that comes up all the time is XOR, right? Exclusive OR. This one is sometimes in programming depicted with a caret. I'm not going to write the caret because it's too confusing with our other triangles. But in the case of discrete math, we indicate exclusive OR with a circle with a plus in the center. So that's exclusive OR Q. And exclusive OR means the output is 1 if exclusively one of the inputs is 1, right? So 0 or 1, the output's 0. In this case, exclusively one of the inputs, Q, is 1, so the output is 1. In this case, exclusively one of the inputs is 1, so the output is 1. In this case, it's not exclusive. They're both 1, so the output is 0. So that's exclusive OR. And these three functions, they're not special in the sense that they're any different from the other 10 binary functions that exist. They're special in that we use them a lot. In fact, exclusive OR, when you guys get into CS51 next semester, I'll show you how we use exclusive OR to build the adding structures that we have in most modern processors. And actually, we won't do it in this class, but you can prove that with and not, you can create a NAND, and with a NAND, you can build any circuit that could possibly be built. And a lot of modern processors are nothing but NAND gates, right? So these are the building blocks for everything else that we do in computing. That's why they're important. Remember, if you have any questions, ask them below in the forum.